Hello, everyone. It is Friday, a little after 3 p.m., and you know what that means. It is time for our live version of your daily equation, in which in the live version, we talk about equations, but basically anything else that you feel like talking about. Most of the time, we do talk about science, quantum mechanics, relativity, Einstein, string theory, unified theories, and so forth. You know, it's funny as I sit here and I realize that we never talk about what's happening in the world. Maybe you're tired of hearing all about that and seeing it all in the news, but man, oh man, what an insane period of time we are living through in the United States. And all I can say to the rest of the world is, I'm sorry. There's nothing more that can be said. What a disgraceful situation we have in this country right now. So anybody want to talk about that, I'm happy to. But let's go to the rarefied, beautiful, pristine, elegant realm of math, physics, and the universe, just to have a little bit of mental respite from everything that's happening in the world. So I'm going to jump right into some questions. And let's see, what will I begin with? Well, Andrew Haney asks, when was the first time that the fourth dimension was introduced, and what was the scientific motivation for that? And I understand exactly what you're asking, Andrew. When was the fourth dimension introduced as an idea in physics? I think is really what you have in mind there. I'm guessing that's what you have in mind. But mathematically, people were thinking about shapes and spaces that could exist in any number of dimensions long before the fourth dimension was introduced into physics. So people like Riemann, Gauss, Lobachevsky, these were great mathematicians back in the 1800s. And you know what mathematicians do? They write down the equations to describe things that you can first visualize and see, and then they're motivated by the language of mathematics to generalize the insights that they have in the ordinary three dimensions that you can see to higher dimensions. So Riemann, who really wasn't thinking about physics applications. That's not completely true. Riemann did have some of his thinking oriented by physics, but to first approximation, for non-physics reasons, Riemann and others began to think about higher dimensional geometrical shapes. How do you describe the curvature of a higher dimensional geometric shape? How do you describe distances on a higher dimensional geometric shape? And so the fourth dimension was introduced way back. In physics, it really came to light through, we often think Einstein, but it was really Hermann Minkowski. Hermann Minkowski was Einstein's teacher, Einstein's professor, famously called him a lazy dog, thought that Einstein was not going to really achieve anything with his life, at least not in science, but man, was he wrong. That's perhaps the worst prediction in the history of being a professor. My goodness, makes us all feel a little bit better. But Minkowski did have the great insight. Once Einstein put forward the special theory of relativity, it was Minkowski who said we should really think about space and time unified together, three dimensions of space and one dimension of time. And the reason he came to that realization is because Einstein's insights showed that motion through space affects your passage through time. Let me say that again, because that is a deep, mind-blowing sentence. Motion through space affects your passage through time. Nobody thought that before. According to Newton, you can move through space any which way, and the temporal quality, the time, it just elapses the way that it always would. Einstein said that's not true. If you move through space, then someone who's watching you will note that your clock is ticking off time more slowly than it was when you were stationary. Motion through space slowed your passage through time. So Minkowski says we now have a deep connection, unexpected deep connection between space and time. Let's knit them together into a four-dimensional structure called space-time. And within that rubric, the equations that Einstein gave us have their most elegant and economical formulation. So that's where it happened in physics, and that's the scientific motivation for that. Let me go over, I saw some question that I liked in Oh yeah. Well, so Jessica from Wichita asks, when you talk about the equations of the universe, are you referring to equations that are somehow out there, part of the universe, or are you describing something that we humans make up to describe the universe? So yeah, it's a very deep question. Is math a description of the world, or is math part of the world? And by world, I mean reality. And I don't know the answer to that question. Nobody knows the answer to that question. In the course of my own career, my perspective on that has shifted a number of times. There have been occasions where you just sort of feel that the math is out there and all you're doing is revealing it. And for Einstein, of course, you're revealing a masterpiece, sort of like the way sometimes people describe the sculptures that are created by the great, say, Renaissance sculptors as being embedded in the marble. And all the sculptor is doing is chipping away the excess material to reveal this masterwork embedded within the marble. Or is it that the marble just has no internal fundamental structure and it really is the artist who is sculpting out of that chaos, if you will, something of great beauty and great order? So it's kind of analogous to that question. My view now, and it's been this way for a while, so maybe I'm done waffling back and forth on the issue. My view now is that math is a language. It is a language of human invention. It's a language that's particularly good at articulating patterns. And because the world happens to abide by patterns, I'm talking about the patterns abstractly, that 2 + 2 = 4, or the pattern of the moon going around the earth at a certain regular rate, or the earth going around the sun at a regular rate, or when you throw a ball through the air, it goes in a shape that is repeated over and over again when you throw the ball over and over again. These kind of patterns are ripe for articulation, ripe for description in the language of mathematics. And that's what we do as physicists, try to find those equations that describe those patterns. So I would put it that way as of today. I would say that it's not that the math is actually out there, it's a language that we invent to describe what is out there. And I should say that question brings to mind a question that hasn't been asked right here, but it's very similar to that question, which is, am I inconsistent? And someone has called me on this. Am I inconsistent in my description of the universe? Because oftentimes I will speak as though the laws of Einstein, general relativity, the laws of Schrodinger, quantum mechanics, the laws of Newton, classical mechanics, I often describe it as if those laws govern the universe, as if they are somehow there and they are enforcing the mathematical description. And if they're there enforcing it and they are transcending human presence, if the laws are governing the world, it's not we humans are governing the world, then haven't I now said something inconsistent? On the one hand, I'm saying the mathematics is a human invention. At the other hand, I'm saying that the math is governing the universe. And I'm not trying to say that we humans are governing the universe. So what in the world am I going on about? Well, it's often just a softness of language that I think most of us understand. If I was being really precise, here's what I would say. And if ever I say something in these sessions or others that feel inconsistent on this point, come back to this description. My view is there are laws. There are laws out there that transcend human presence. I don't know the right language for describing those laws. As of today, the best language that we have is mathematics. And therefore, we use mathematics to articulate the laws of general relativity and quantum mechanics and classical mechanics and so forth. But that's a description. The laws are out there. The laws do govern. The laws are controlling in the sense that the processes of the universe don't step outside of those laws. Now, can I prove that? I can't. What do? We look at the enormous mountain of data accumulated, in some sense, since the beginning of human civilization. And we have never found repeatable examples in the world in which the patterns were violated. Sometimes we didn't understand the patterns and we needed very intelligent individuals to come along and give us a deeper understanding of what the patterns are. And they phrase those insights in the language of mathematics. But to my mind, those mathematical sentences are approaching an explanation and understanding of the laws that are out there. But I'm not saying that the laws themselves are necessarily framed in the language of mathematics. Maybe they are, maybe they're not. So from that perspective, it's consistent to say that mathematics is human invention, the language to describe the patterns. The patterns described by laws are out there. What's the real fundamental way of describing those patterns? I don't know. Maybe it is math, maybe it is not. On that, we do not have an answer. Okay, what else do we have? So Asit Dash asks, what are the future goals of CERN's Large Hadron Collider? Which is an important question to ask. A lot of money was put into the collider, and the primary initial goal was to find the Higgs particle, the Higgs boson, this little packet of the Higgs field, which Peter Higgs conjectured, surmised, would be a field uniformly filling space that would exert a kind of molasses-like tug on any particle moving through the universe. And that molasses-like tug would be the origin of the mass of each and every particle. So there was a big puzzle before Higgs came along, which is how do fundamental particles acquire mass? Because the mathematics seem to suggest that all particles should be massless. The mathematics relies on certain deep symmetry principles, and the symmetry principles seem to demand that the particles were massless. And Higgs's resolution to this was, he said, look, the particles are massless fundamentally from the get-go, but once those particles are moving through space, they acquire mass through an interaction with the environment, not because they intrinsically have heft per se, but rather because they're interacting with the quality of the environment. As the particles move, they are like little pebbles trying to make their way through molasses. And just as the pebble will feel a drag force from the molasses, particles feel a drag force from the Higgs field. How do you try to prove this crazy sounding idea? Well, the theory that Higgs put forward also shows that you should be able to slam space by having particles collide at high energy. And when you slam, in some sense, empty space, it can cause the Higgs field to jiggle. And if you jiggle it in the right way, little particle sprays will fly off the Higgs field, sort of like if you slap the surface of water, droplets of water will spray outward. And the droplets of the Higgs field that would spray outward would be Higgs particles. So the Large Hadron Collider was built to try to find those Higgs particles. And as everybody here, I hope, knows, that was an incredibly, remarkably successful undertaking. 2012, we found the particle. Okay, good. So the question then is, what's next? Now, what we hoped would be next would be the detection of so-called supersymmetric particles. These are particles put forward by a different theory, a theory called supersymmetry, whose development goes way back to the early 70s. It's another type of symmetry, first discovered actually by people studying string theory, just saying. It was then generalized to other areas of particle physics that don't have to have strings in them at all. But it's a very general phenomenon that for every known particle that we have so far detected, supersymmetry requires that there's a partner particle. So for electrons, you should have selectrons. For quarks, squarks, neutrinos, sneutrinos. Don't look at me like that. I don't make up the names, all right? I just follow the conventions. And so the hope was that the Large Hadron Collider would find these partner particles to the known particles. And that was the next goal. And the fact of the matter is, we've been at it for some time, and none of the supersymmetric particles have been found. And that's kind of sad at some level for many of us. But I mean, nature is not constructed to make physicists happy. That's something that Steven Weinberg has emphasized to us repeatedly. But yeah, it would have been nice to find those particles. We still may. If I look back at my own career, I would say that 90% of the papers that I've written in one way or another touch on supersymmetry. So how sad would it be if this quality in the mathematics is not realized in the real world? Thankfully, some of my papers are just in the mathematical side of things. So whether or not the particles are real, the mathematical insights derived from the symmetry, they're unassailable. But yeah, it would be great to find the supersymmetric particles, circumstantial evidence, even for string theory. So my hope is I see that that's what will be next, but the window of opportunity is shrinking and shrinking. So I wouldn't hold your breath on that one. And then after that, we may need really to upgrade the Large Hadron Collider to a machine that has greater energy reach. China is talking about the possibility of building the next detector, the next accelerator with detectors, of course. And that may be 10, 20 years into the future. So it could be that in the worst of all circumstances, particle physics may, at least at the level of the energy scales that we hope to probe ever higher and ever smaller length scales, that may go into a hiatus in the not too distant future as we wait for a machine that can really take the leap to ever higher energies. So I don't know the answer, but that is certainly one possibility. Perhaps that's the least happy one. But look, we could still find the supersymmetric particles. We could still find unexpected things. In fact, that's probably the best answer to your question, Asi. What's next? I don't know, but I hope it's a big surprise. We live for the unexpected results that force us to go back and rethink our theories. So that may be hopefully what happens next. Yash Shah asks, can general theory of relativity be questioned on the basis of Hawking radiation? And the answer, Yash, is absolutely not. Absolutely not. So Einstein's general theory of relativity is a classical theory. It is a theory that doesn't know about the quantum nature of the world. Einstein developed the general theory of relativity in 1907 to 1915. Those were the years in which a parallel track was developing quantum mechanics, but Einstein wasn't waiting for quantum mechanics to be completed before he dove in to try to come up with a new description of the force of gravity. So Einstein's theory doesn't talk to quantum mechanics from the get-go. And Hawking radiation emerges only when you meld certain aspects of quantum mechanics with the general theory of relativity. So it's not that Hawking radiation contradicts Einstein's theory. Hawking radiation is a natural outcome of extending the general theory of relativity to include certain quantum mechanical qualities. So in that sense, they are naturally linked together in a progression from the classical description to the description that goes one or two steps further to bringing quantum mechanics into the story. Okay. Hello, Professor Greene. Sami Saeed asks, if we go into space and rotate in the opposite direction of Earth's rotation and twice the speed, isn't that time traveling? So the answer to that question is yes and no. I kind of think from the framing of the question, Sami, that what you have in mind is that scene from Superman, where Superman kind of circles around the Earth really quickly in the opposite direction to the Earth's rotation and somehow goes backward in time. And I think the intuition there is that if the Earth is turning this way and time is going forward, then if time was going backward, the Earth would kind of go the opposite direction, or at least if we go the opposite direction, we're going backward in time. And none of that holds any real water. The orientation of the spin of the Earth, whether viewed, say, from the North Pole down as counterclockwise or clockwise, is not what determines the arrow of time from the past toward the future. Instead, the arrow of time from the past toward the future, as you can see in your daily equation, maybe it's the last episode that I did. I think it was number 32 or something. That comes from considerations of entropy, second law of thermodynamics, the Big Bang being a highly ordered state, and so forth. And those qualities of the world are not dependent upon the very specific orientation of the Earth's spin. Now, there is a way of interpreting your question, which does yield a more positive result, which is whenever you go into motion, your clock will slow down relative to my clock. So if I'm looking at you in motion, then your clock is going slow. So if you then return toward me, undergoing some round trip journey, some accelerated trajectory to return to the starting point, you will have not traveled into the past, you will have traveled into the future, because my watch will have ticked off more time than yours. And by my watch, I mean everything about me. Time itself will have elapsed in a greater duration during your journey. So you will have jumped into a later time period. And so there is a kind of time travel that comes from precisely what you describe, that kind of motion, but it's not time traveling toward the past. Although you didn't actually say toward the past, so maybe that's what you have had in mind. It's time traveling toward the future. So Sami, if I misunderstood your question, you should come back at me. I'm happy to revisit it if I didn't interpret your question correctly. Paul C asks with 8 stars, and therefore definitely requires me to answer. Hi, Professor Greene. How was the Big Bang low or even zero entropy? And the quickest answer is I don't know. Yeah, I'll go a little further than that. Can't help it. So we make an assumption that the Big Bang was highly ordered, low entropy. Why do we make that assumption? We make that assumption because it's the only way that we can articulate. It's not the only way, but to my mind, it's the most convincing way that we have ever come to for articulating why there is a direction to time, right? So we all know that there are these qualities of the world that are asymmetric in time, various things, right? We age, we don't unage. And you guys, maybe it's not you guys explicitly, but there are many people on my videos who remind me that I am aging. I really do appreciate that. So I love it when you guys tell me how old I've gotten. So thank you. I really do enjoy that. But yeah, you're just reminding me of this important physical fact that time has a direction to it. It goes from the past toward the future. But even more mundane things, they become hackneyed after a while. But glasses shatter, they don't unshatter. Eggs splatter, they don't unsplatter. Candles burn, they don't unburn, right? A gazillion things that have a temporal orientation to them. Why in the world do they have that temporal orientation? And if you look at the laws of physics themselves, as I emphasized in episode 32, the laws treat past and future on equal footing. So you can't just appeal to the laws and say the laws don't allow glasses to unshatter or people to unage. No, the laws in principle do allow that to happen. Then what do you do? Well, this is what took us to this idea of entropy, that there is a natural tendency simply by the law of large numbers for systems to go from order to disorder, because to be disordered is a very easy configuration to achieve. There are so many ways to be disordered. An ordered situation, well, that's highly organized. That's hard. That requires everything to be in its proper place. And therefore, it's very difficult, comparatively speaking, to be ordered. And so as particles are randomly moving around, of course, they're going to move toward disorder because it's so much easier. There's so many more ways to be disordered than ordered. But that only really holds any water if there was a state of order to begin with. If you had a state of disorder at the start, at the Big Bang, then you'd have disorder all the time. You need order in order to anchor the arrow of time, so that as time unfolds from the Big Bang, you are creeping up toward ever greater disorder, but along the way en route, today, you still have some residual order. That's why we make this assumption. Now, can we explain the order of the Big Bang? I've tried. I've written papers on this. None of them really are convincing, because oftentimes you find that you're sneaking in an assumption of order in a different language or a different mathematical formalism. So I would say that today there are some people who say it's not a question that even is worth asking, because they say, look, we have one universe. When people say that the Big Bang was highly ordered and therefore that's very unlikely, because ordered states are very unlikely, they're basing that on intuition from everyday life. Yeah, it is unlikely that if I take 100 pennies and I throw them on the floor, they will land in the ordered state of all heads. Very unlikely. If I throw those pennies, it's far more likely that they'll land roughly 50 heads and 50 tails, because there's so many ways in which you can get 50 heads and 50 tails. Someone told me how to pronounce that number. Maybe it was on your daily equation, 100 octillion. Someone told me is how you pronounce that number. So it's, much more easy, but that's in everyday life with pennies or other familiar structures. When it comes to the universe, what do you mean when you say that it was unlikely for the Big Bang to be ordered? Did you have many Big Bangs and you looked at all of them and you found that the preponderance of examples had high disorder and very few had high order? Is that the sense? Do you imagine that you're throwing darts at possible universes from a range of possibilities, and for your dart to hit the universe that has an ordered Big Bang is just unlikely because there's so many more universes that have a disordered Big Bang? What do you mean by unlikely? In the most straightforward interpretation, you can say, look, if there's one universe, you can say, if these ideas are correct, that it began ordered with 100% certainty. It was ordered and there's only one universe, period. That's it. So you have to be careful when you generalize from unlikely events in everyday life to unlikely events when it comes to the universe as a whole. So look, if we could find an explanation that really gave us some insight into a process that required or ensured or entailed that the universe was highly ordered at the Big Bang, we'd all be happy. We'd all feel like we'd made progress. But if we don't have that explanation, it may simply be telling us that we're asking the wrong question, that the orderly state of the Big Bang may have been an environmental state that we just need to accept as is because the universe happened once, and for whatever reason, there's something rather than nothing, that something came into existence in an orderly state. That could, however unsatisfying, that could be the answer. Sergio Muntian. Hi, Professor Brian. Can you explain how Einstein's theory of gravity applies to us or objects sitting on the surface of the Earth? Yeah, I can. So the imagery that we often use in the general theory of relativity is, say you have a star and the presence of the star warps the environment around us. We often give a two-dimensional image for that, which is not perfect by any means, but you have, say, the sun and you have this warped shape underneath it. Now, there is no underneath the sun. What's really happening, it's warped all around and so forth. But let's use that imagery just to have something to hang my answer on visually. The Earth does the same thing to the environment. And what that means is our bodies want to slide down that indentation in space-time. But what happens is the surface of the Earth gets in our way. Like right now, my body wants to slide downward, but my body is hitting this chair, and this chair has legs that are hitting the floor, and the floor is hitting the surface of the Earth. The Earth is getting in the way. So you can think about it as if there's a slide that, in the absence of the Earth's surface, if the Earth's surface they were compressed, so it was 100 miles closer to the center of the Earth, my body would want to slide all the way along that from where I currently am. But because the Earth's surface is there, my body slams into it. So the upward force that you feel right now, that I feel right now from whatever structure is supporting us, that upward push is happening because general relativity is trying to guide our bodies along the indentations in the space-time fabric that the Earth creates, but the surface of the Earth is getting in the way. That's certainly one way of thinking about it. Now, as a caveat, I'll note to you that near the surface of the Earth, the better description is not really that space is warped, it's actually that time is warped. I haven't actually discussed this in your daily equation yet, but I kind of should, because it's a beautiful idea and it's one that doesn't get as much play as it might. But when you try to understand ordinary gravity that we experience from Einstein's general theory of relativity, it's the temporal part of the distortion that really captures the kind of gravity, the relatively weak gravity that we all feel. And so in some sense, what Einstein tells us is that time elapses slower and slower and slower toward the surface of the Earth or toward the source of gravity more generally. And objects, according to Einstein, are drawn toward those locations where time elapses more slowly. So rather than thinking in the spatial example, which is a fine way, so I'm not trying to undermine my own answer here, but in the spatial example, I had our bodies trying to slide along an indentation as if it was a slide in a children's park or a water slide in a play world type of environment. But a better description is that we're trying to move toward the direction where time elapses more slowly. So maybe the cosmetics industry is a better metaphor, right? Cosmetics industry, we spend billions of dollars trying to look as though time is elapsing more slowly. Einstein's theory fits in with that urge because the geodesics in a space-time environment point in the direction of the slowing of time. That's actually what happens in the general theory of relativity. And as we say that, I think I'm going to have to keep that in the back of my mind. I realize I've never given the geodesic equation in general relativity. I don't think I've given you the equation d2x mu d tau squared plus gamma mu nu lambda dx nu d tau dx lambda d tau equal to 0, where gamma is the Christoffel connection. Good, I got our equation in. I'm happy now. So that equation tells you the shortest possible trajectory in a space-time environment with a connection gamma determined by a metric g. And what I just described is what happens in the vicinity of a body that doesn't have a fantastically strong gravitational field and a body that's not moving relativistically. So that is the answer to your question. Deng Jia says that should be our next daily equation. Deng, I agree with them. I'm just not sure when exactly that will be. So Captain Benzino, it's a long question, so I'm taking a risk on you, Captain Benzino. I'm going to read it without knowing whether it's a question that I want to address. But here we go. Maybe dipping into science fiction here. Uh-oh, I'm starting to worry. But black holes, all right, now I'm feeling a little bit better, must hold infinite mysteries. Okay. Is it theoretically possible to create a material or substance with elastic properties to probe and send a signal? So I think what you have in mind there is kind of unfurling some kind of object, maybe like a big piece of rope or a bungee cord that could be rolled out from a safe distance from a black hole toward a black hole in order to probe its properties. And Captain Benzino, I don't know if that's ever going to be practical in the real world. Probably it will be if life persists long enough. In fact, there's something called the Penrose process that Roger Penrose, real iconic figure in math and physics. And by the way, I'm going to answer Captain Benzino's question, but just comes to mind. I was thinking that it might be fun in some of these your daily equations if I bring in some of my colleagues that you maybe read their books or read their ideas to sort of have an informal conversation of their favorite equations and some of the insights into the world that are due to them. So if you would be interested in me doing that on occasion, as opposed to me just talking to you straight out, let me know, because I'd be happy to do that. But the Penrose process is one in which, in principle, if you have a rotating black hole and you can somehow lower down a bucket toward the black hole, you can in some sense scoop out energy from the black hole through this process. So people have thought about this idea, at least hypothetically, Captain Benzino. Moreover, when you try to understand the entropy of black holes, the disorder of black holes, one of the ways of doing that is you imagine lowering one bit of entropy into a black hole, and you ask yourself what happens when the black hole absorbs that disorder. What happens is the event horizon grows by a minimal amount, a Planck area divided by 4, which is all just to say that even though you thought of this in a kind of science fiction-y way, we physicists often make use of thought experiments today that invoke the very kind of setup that you envision, lowering things into a black hole. So the answer is yes, very much so, at least from a theoretical standpoint. It's been very useful to think that way. practically, I don't know. We'll have to wait and see how things evolve toward the future. Okay. What do we have? Oh, there's a 0.99 question. Maybe I'll come back to that if but let's see. Um, so Leandro Sheppers asks, "Hello, Professor Green. What happens to the energy of a photon that gets redshifted by the universe that is expanding?" And that's absolutely a justifiable question. You know, we often say that when you have a photon in an expanding environment, what happens is that the photon itself is somehow sufficiently woven into the threads of space-time that as the fabric expands, the photon itself gets kind of pulled outward like an accordion, and that stretching of its wavelength lowers its energy, makes it head more toward the red part of the spectrum, assuming that was on the other side of red. Redshifting can be an increase in energy if you're on the other side. But if you're on the higher energy side of red, then the redshifting takes you to the lower energy. So where does the energy go when that happens? And the answer is that it goes into the gravitational potential energy. You see, you have to remember what happens when a baseball is thrown upward. As the baseball is thrown upward, it goes slower and slower. Where does the energy go? It goes into gravitational potential energy because the baseball is fighting against gravity in some sense. And gravity is also what's responsible for the expansion of space. So, in some sense, the stretching of the photon is going into a kind of gravitational potential as well. So that's the answer to the red shifting energy of a photon in an expanding universe. Okay. Um, let's see. Hackers Lab. Hi, Professor. What do we mean by a tear in space? And how does string theory explain these and then repair the tear in space time? Always a fun question for me to address, as I think Hackers Lab knew that I would be open to that question since I was the person with a couple of colleagues who wrote the first papers on these ideas. But so a tear in the fabric of space, what does that mean? Well, literally what we mean, not literally, what we mean is, I hate it when people use the word literally wrong. What we mean is there are shapes that cannot be smoothly deformed one into another. There are other shapes that you can smoothly deform one into another. For instance, if you gave me a beach ball and it was made up of elastic material, I could smoothly stretch the beach ball and turn it into more like an egg shape. So the beach ball and the egg shape are what we say they have the same topology. They have shapes that can be smoothly deformed. Continuously is probably a better word, from one into another. There are other shapes where there is no such continuous motion of that. For instance, if I give you a donut and a ball, to turn the ball into a donut, you've got to somehow rip an opening inside. There's no way that you can continuously deform one into another. And so when we say that space tears, what we really mean is the topology, the shape of space is changing in a manner that cannot be accomplished through a continuous process. So have in mind going from donut to ball or ball to donut. You've got to tear or you've got to rip open the shape. If you're going from donut to ball, you've got to kind of cut along one of the circular parts around the center of the donut, and then you can turn it into like a banana shape, and then you can reshape that into a sphere. So what we found is in string theory, the universe can evolve continuously, smoothly between two different shapes that are topologically distinct, shapes that cannot be smoothly, continuously transformed into one another. And string theory protects us from what otherwise would have been a disastrous consequence in, say, the general theory of relativity, where space cannot tear. And that's really what we mean by the fabric of space ripping, and what we mean by string theory allowing these processes to happen. Alice says that she's getting hungry. I guess that was my reference to donuts. Alice, I'm kind of hungry too. I'm wondering, if we did these sessions long enough, we should set it up in such a way that everybody gets dinner delivered, regardless of where you are in the world. That would be we will do that, no doubt, one day, not yet. But I am tempted to bring my dinner to these sessions, as they seem to go longer week after week. Niraj asks, Professor, does the size of a black hole increase as it eats spacetime? There's a culinary theme that we see threaded through a number of these questions now. So we're back to questions of imbibing food. So does the size of a black hole increase as it eats spacetime? Well, I don't know exactly precisely what you mean by eating spacetime, but I would say that when the black hole eats material objects, if you throw those donuts into a black hole, the donuts have mass, they have energy, and as the black hole absorbs the energy, the black hole grows in size. Because remember that the radius of a black hole, and by radius, there's a precise meaning, but roughly speaking, you can think of it as the size of the black hole. It's related to the surface area of its event horizon. But the radius of a black hole is proportional to its mass, right? R equals 2gm over c squared. That's the formula for the radius of a black hole of mass m, where g is Newton's constant and c is the speed of light. So if the mass goes up, the radius goes up. So as the black hole eats stuff that increases its mass, its size does increase. I'm not exactly sure what you mean by eating space-time. Oh, I see. And you have a second part of the question. Can it be used to test if space-time is made of particles? So you really do mean the eating of space itself. And I'm trying to think how to interpret that. I'm not exactly sure how to interpret that statement. It is the case that, according to Stephen Hawking, the reverse happens, that a black hole can have particles radiated toward infinity. That's kind of the reverse of eating. I don't want to get into the kind of gross description that is running through my head right now when the concept of reverse eating is brought to bear. So I will exercise restraint. And I don't know if my wife is listening to this, but I hope that you're proud of me for not saying what crossed my mind a moment ago. But as the radiation comes out of a black hole, the black hole is emitting energy, emitting food, if you will. And because of that, its size gets smaller and smaller. So it's kind of the reverse of what you're talking about. The black hole is giving back space-time because now you have more and more space outside the event horizon of a black hole. And as it's giving back that space, the way it does so is it's emitting particles toward infinity. So you kind of see the interplay between the size of a black hole, the amount of space outside of it, and the radiation that it's emitting. So I hope that approaches an answer to the question that you have. Again, come back if somehow that does not satisfy you. Prayag Dash asks, what is mirror symmetry? And I think you guys conspired today and said, let's ask Brian Greene all the questions about the stuff that he did. So he'll feel good today. So thank you for that. It does feel good for you to ask about the stuff that I've been involved in. So mirror symmetry is a property that I found with my colleague Ronan Plesser, who is now at Duke. This was in the late 1980s. And I should say there was another group that found effectively the same idea from a very different perspective. That was led by my colleague and friend Philip Candelas, who's now at Oxford, and various of his students. I'm trying to remember. It's been a long time. Monica Linker, Rolf Schimrick, I believe, were on the initial paper that they wrote back then. And the insight that we found is that when you're looking at the extra dimensions in string theory. So in the most conventional formulation of string theory, there are 6 extra dimensions. Note to self, I should do your daily equation on extra dimensions. I think I will do that. But you have these 6 extra dimensions in string theory. And what we found is the shapes of those extra dimensions come in pairs that look completely different. Technically, they're topologically distinct. They're completely different geometrically, topologically, and yet they give rise to exactly the same physical properties in a universe in which they are taken to be the extra dimensions. And that's highly unexpected because in the general theory of relativity, even if you don't understand the mathematical details, what we have been describing over the course of your daily equation, but even here today, is the geometrical shape of space-time dictates the physical processes that ensue, right? If you've got a shape like this, then the shortest trajectories, which are the geodesics that particles will follow, will be different from a shape which is radically different from the initial shape. But surprisingly, we found that there are pairs of shapes of the extra dimensions that look completely different to a geometer, to a mathematician, but are completely identical from the standpoint of physics. Now, why is that interesting? Well, there's a lot of interesting things there, but the first application, and this application we actually wrote down in our original paper with Ronan Plesser, but it was really Philip Candelas and another team that put this into action in a spectacular way. We found that there are certain mathematical questions about these higher dimensional shapes that can be ferociously difficult to answer on one geometrical shape. But if you make use of its partner shape, the mirror partner, that looks different but has the same physical properties, many questions that are horrifically difficult to answer on this shape, when you translate them into a question on the mirror shape, the question becomes easy to solve. In essence, you have a dictionary to go from difficult math questions on this shape to easy math questions on the mirror shape, guaranteed that the answer you get in the easy setup will be the right answer for the difficult setup. And that's a powerful tool, obviously. It's much easier to answer easier questions. And so Philip Candelas and his crew were the first to put this into action. Again, we wrote down the formula in our paper toward the end of our paper, but I never really thought anyone would evaluate the formula. I just thought it was a cool observation to go from hard to easy. But Philip actually put it into practice and was able to answer questions having to do with the number of spheres that you can pack in a certain way into these higher dimensional shapes. Mathematicians had answered very few of these questions. You can characterize the embedding of the sphere into the shape by how many times it winds around itself. And mathematicians had answered the question for the number of such spheres if you wind once, twice. But for 3 times, the mathematicians at that time had not been able to crack that problem. But in our reformulation, the easy question, it winds out that you can easily just write a little computer program and spit out the answer for winding 1, 2, 3, 4, up to whatever number you've got patience for. So I remember there's a wonderful conference in 1991 in Berkeley where a bunch of mathematicians came, a bunch of us physicists, string theorists came to try to understand the math and physics of mirror symmetry. It was a real exciting time. I remember I gave the opening talk at that conference, trying to speak as best as I could at the time in a language that would be acceptable and relevant to both the physicists and the mathematicians, who generally speak completely different languages. You might think we all speak mathematics, but honestly, it's like when I went to Scotland. I met some people in Scotland and I was like, I could understand like only, I don't know, 25% of what they're saying. We all speak English, but man, it was tough. And mathematicians and physicists, it's often the same kind of thing. We got a different dialect going in the way we speak our mathematics. So trying to speak to both audiences is a challenge. But what happened at that conference is some mathematicians came along and they claimed that they had finally cracked the problem of how many times you could embed these spheres with winding number 3, it turns out, into a particular 6-dimensional shape. The quintic hypersurface and complex projective force space. Details don't really matter, but it's just a complicated problem. They had their answer, And the physicists had their answer coming from our work and the work of Candelas, and the answers were different. Now, of course, the mathematicians thought the mathematicians were right. The physicists thought the physicists were right. And we left that conference not knowing which group was correct. A few months later, the mathematicians send around an email saying that they found a computer bug in their code. And when they fixed it, lo and behold, the answer they got agreed with what the physicists had been saying. So physics triumphed. It was a very exciting time. And again, the mathematicians at that time had difficulty going to winding number 4 or 5 or 6, but we physicists, it was just a matter of hitting a button on a computer and spitting out the answer. So it was a very powerful realization, this mirror symmetry, for solving a collection of interesting mathematical problems. Anyway, so you brought me back 30 years now to some exciting times in the early days of my own career. So thank you for doing that. Okay, let's see. So Lion King asks, in the last daily equation, you said that entropy can actually decrease if a system has a small configuration, like I did, if you remember. I don't know if I did it. I think I did. I did like 10 pennies. Yeah, I think I did do that. I did 10 pennies. And we found that if you throw the pennies over and over again using this computer code that Danny Swift wrote for me at the World Science Festival, so that was sort of fun to have that, if you allow the computer to throw the pennies on the floor, on the table 10,000 times, a certain number of times, you see an ordered outcome. All heads or all tails. So entropy in some senses is going down. It's a metaphor, of course, but the metaphor is that on occasion, random processes can yield ordered results. It just happens on occasion. So the question that Lion King asks is it possible, therefore, for a particle to travel back in time if you're sort of in a small enough region or a small enough number of particles? And I understand the intuition behind the question, Lion King, but I don't mean to be flippant, but it's a conflation of two ideas. And this is a really important point. If time were to go backwards, if you actually wind a film backwards, then indeed you can easily go from disorder to order. And I showed you films of that in your daily equation. You've seen them on your own. You wind the film backward and the shattered glass does unshatter. The egg does unsplatter. So it leads you to the intuition that going to lower entropy is the same as going back in time. And that intuition is wrong. It's a natural intuition. I get it. It really comes from thinking about, as I just mentioned, winding films backward in time. But that's not the right way to think about things. Lowering entropy in the manner that I was showing you is a forward-directed temporal process. I was truly imagining throwing those coins with time ticking off in the ordinary temporal direction and noticing on occasion, holy smokes, I got all heads. Entropy went down. Nothing to do with traveling backward in time. It's simply the fact that entropy and its increase is a statistical likelihood, not an ironclad law. And that's the point that I was making. There are these ironclad provisional laws, be they Newton, Einstein, Schrodinger. When we write down those laws, we're imagining that the laws hold. Whether they're the right laws is a separate question. But if they were the right laws, they would hold. They would always hold. They would never not hold. That's what we mean by the traditional word law when applied to the universe. The second law of thermodynamics, however, changes the meaning of law a little bit. We are not saying that there's an ironclad, rigid progression of entropic increase. We are saying that there's an overwhelming likelihood of that progression, but on occasion, entropy can go down. Nothing to do with traveling backward in time. Okay. Man, it's going by too fast. I saw one that I liked and it's gone. Alpha Omega Spy asks, how is your mother? Thank you, Alpha Omega Spy. That is so nice of you to ask. She's hanging in there. She's having a tough time, but when you're 92 going on 93, It is difficult. It is hard. But she actually moved from my house to my sister's house in Massachusetts. So she's convalescing there at the moment. At some point, she will be back here. But thank you for asking. Okay, so your question is, since particles do not care about time, why should particles care about natural selection? Why should particles seek to improve themselves? And there are two questions in there. They're highly related. Let me take the second one first. Why should particles seek to improve themselves? So, alpha omega spy, you're framing that in language that I often use too. You're framing it in anthropomorphic language. You're framing it as though the particles have a will, have a consciousness. And you know my perspective, I don't think that they do. So, when we talk about why particles seek to improve themselves, I'd rather reframe it as why is it the case that over time particles can find themselves in more refined, more orderly, more organized configurations? How in the world would that come to be? And the idea here is that when molecules learn a particular unusual trick, when they accomplish on a systematic basis a particular feat, then they're subject to a version of natural selection that ordinarily we apply to living systems, but can equally well apply to non living systems, which is this. So, as particles learn to replicate, make copies of themselves. So, imagine I've got a collection of particles. If that collection of particles can make a duplicate of itself, and the duplicate can make a duplicate of itself, then we find a natural means of taking stuff from the disordered environment and templating it into a repetitive molecular order, a repetitive molecular structure. A parent molecule has children, the children have children, and the way the children come to be is by the parent grabbing raw materials and making a copy of itself. And therefore, you can see that those collections of particles that are better at making copies, for whatever reason, their electromagnetic structure more readily pulls in the same ingredients out of which they're made, their arrangement provides a natural template that allows for a quick replication, whatever the reading, whatever the meaning and reason for that. The point is, when particles get better at making copies, they dominate. They dominate the environment. And if they have a progeny, a child that perhaps is mutated, maybe an interchange of two particles in the arrangement, if that arrangement is better able to make copies and have progeny, then that version will dominate the demographics. So you see a natural move toward more organized structures that comes not because animal species one is battling species two in an arena of combat among living systems, but rather molecule one is battling molecule two in a combat that's taken place right down at the level of particles. And winners of that combat can naturally dominate the world. Now, how does this relate to the fact that the particles don't care about past and future? Well, again, it's coming from, in essence, the order of the Big Bang. The orderly structure of the Big Bang allows for little pockets of order to form. And those little pockets of order, which are in some sense residual order from the Big Bang, can make copies of themselves. And the molecular Darwinism that I was just described can roll on forward. If the Big Bang was a highly disordered state, maximal disordered state from the beginning, if it was a collection of black holes, then we wouldn't have the opportunity for the ordered structures to ever get off the ground. So the arrow of time that I described in the last episode, in terms of the orderly Big Bang, second law of thermodynamics, and drive toward ever higher entropy, is really an arrow of time that would apply to all processes for which we see a temporal asymmetry, including molecular Darwinism. So it's the same answer as in episode 32. Okay. Gem's tone, replicators. Yes, I'm absolutely talking about replicators, but replicators down at the level of collections of molecules. Woody, live at last. Hello, Brian. Chat. Yes, I give you the thumb up, Woody. Feel free to ask a question if you'd like. Naveen Kumar makes a quantum mechanical prediction that the probability that I will see this question is certainly 0. Did you see this question, or do you see this? And Naveen Kumar, I do not see your question. So your prediction is correct. The probability of my seeing it is 0, and I never, ever saw it. Okay, so what else do we have here? I am asked, do we understand space-time fully? If not, then what are the gaps in our understanding of space-time? And I would say that really is the central question for 21st century fundamental physics. We don't, by any means, understand everything about space-time. At best, we understand certain qualities of space-time. We learn those qualities mostly from Einstein's special theory of relativity, general relativity. We learn that time has this weirdness. It slows down in motion. It slows down in a gravitational potential. We know that space also contracts along the direction of motion from special relativity. We know that space warps from the general theory of relativity. But is that the end of the line? No way, not at all. If you were to ask me, what do we even mean by space and time? I can only give you a very rough answer, an answer that's really not much more satisfying than the answer given by Isaac Newton. Isaac Newton basically said, what is time? Didn't give a definition. Isaac Newton in the Principia just says, time flows equably. He's just sort of saying there's sort of equal intervals and a repetitive pattern to the beat of time, but that doesn't give a definition of time. And when talking about space, I don't remember the exact language. Someone can give it to us from the Principia, but when talking about space, Newton's description was again very much focusing upon intuitive characteristics of space, but wasn't telling us what space actually is. So the answer to your question, is we do not fully understand space-time. And the gap is we don't have a definition. We don't have a definition for space or a definition for time, some fundamental definition. I think, as I said before, my suspicion is that the next leap in understanding will be when we can identify ingredients that make up space and time, sort of molecules and atoms of space and time. And loop quantum gravity is an approach that believes that it has insight into that question. I'm less clear that those insights are the right direction to go, but it's just to say that in loop quantum gravity, there's some thought about what the atoms of space and time might be. In string theory, in recent days, by days, I mean the last few years, there's been insight into the relationship between quantum entanglement and, in a sense, the threads of the space-time fabric. And that's an exciting development, but these are all tentative. And so the next big breakthrough will be moving from these tentative ideas to ones that have a more solid mathematical and ideally observational footprint. So that is vital to have a full understanding of space-time. We are certainly far from that at the moment. All right, let me just look over from our Twitter side of things. I haven't been giving much Twitter love in the last hour. Okay. Amanda says, it seems like every single event, when analyzed specifically enough, can be seen as an unlikely event. And I agree. So why don't we take that up with the pennies, because that's an important point. And I remember when I was doing episode 32, in the back of my mind, Amanda, I was wondering if I had said enough to address that question or not. And I don't think I did. So let me point out the following. When you throw pennies on a table, 100 pennies, every outcome is just as likely as every other outcome, in the sense of specifically delineating the disposition of each and every coin. So imagine the coins are numbered 1 to 100, and every outcome, if you want to specifically delineate it, requires me to say coin 1 heads, coin 2 heads, coin 3 tails, coin 4 heads, and onward up to coin with the label 100. Let's say it's heads. Every configuration delineated at that level of specificity is just as likely or just as unlikely as every other. Because just as a single coin has an equal probability of being either heads or tails, then if you got 2 coins, each of them has an equal likelihood of being heads or tails. So whatever outcome you have is just as likely, just as unlikely as every other. Now, framing it that way, you begin to say, well, whoa, what about the whole entropy stuff? What about the whole statement that it's more likely to have 50 heads and 50 tails? How do we square that with, as Amanda says, every outcome being highly unlikely? It's 1 out of, 100 octillion possibilities, each and every specific outcome. What we do is we group together certain outcomes and we consider them part of the same group of possibilities. So when I talk about 50 heads and 50 tails, I'm not worried about whether the first coin is heads or tails or whether the second coin is heads or tails. I don't care. All I care about is the grand total number of coins that are heads and the grand total number of coins that are tails. And there are an enormous number of configurations in that group. Because again, as I described in the episode, if you watched it, I don't care whether it's the first 50 coins that are heads and the second 50 that are tails, or if, 35 of the first 50 coin are heads and the other heads come from 15 of the remaining 65 coins, right? So what only matters to me is the grand total number of coins that are heads and number of coins that are tails, not the specifics of which particular coin is heads and which particular coin is tails. And by grouping together the possible outcomes, now I have a different kind of comparison that I can make. I can say to myself, how many outcomes are in that group versus this group? And if one group, say, has only one member, like all heads, one sole member, every single coin is heads. Whereas a group that has a total of 50 heads and 50 tails has 100 octillion members because of the different rearrangements of the individual coins that can fit the bill of 50 heads and 50 tails. So that's the way we get the skewing of the odds, not by looking right down at the specifics of any individual outcome, but rather by grouping the individual outcomes according to a more macroscopic quality. In this case, the net number of heads and the net number of tails. Very good question, Amanda. Another one, I'll just for the heck of it, since I'm over there on Twitter. Zalex Boy 92. I have a question regarding, that was a very New York accenty, so I'm going to rewind the film. We'll just edit that out of the finished. No, we don't edit these at all. So Zalex Boy 92. I have a question regarding your illustration with the change of trajectory of each and every piece of the wine glass in order for the glass to reassemble. Would gravity also be required to be at an opposite for this to happen? Wouldn't that break Newton's second law? And the answer is you don't need gravity to be opposite. So if you actually go to episode 32, I spell this out mathematically. I won't do the math here. But in Newton's second law, where the force is due to the force of gravity, so you have the force of gravity is mass times acceleration. When you look at the acceleration, d2x dt squared, for the original trajectory of the splattering, shattering glass versus d2x dt squared for the reverse motion, you wind up getting two minus signs in the reverse motion because x of the reverse motion is simply x of t of the reverse motion is basically x of minus t of the forward motion. T goes to minus t. Every time you take a derivative, you get one more minus sign. You take two derivatives, minus times minus is plus. So the reverse run trajectory exactly satisfies Newton's second law with the ordinary, everyday version of gravity, not a reverse version of gravity. That's how it works. So Dang Joss says, I don't agree with that gravity matters. I'm not sure what Dang is referring to. Maybe what I said? I don't think so. I was saying that gravity matters too, but you can't change its orientation. Or maybe Dang Joss was referring to something in the chat. Maybe you guys are having a side conversation that I missed. But in any event, Paul C. asks, hi, Professor Greene, will you be putting episode number 24 up on Your Daily channel again? So episode number 24 has become this kind of enigma, this legendary episode. Did it ever really exist is the question that we could ask. Now, it's far less mysterious than that. It's not like the, what was it in the Maltese Falcon? Right? It's the MacGuffin, right? It's the MacGuffin episode. No, it really did exist. And I'm pretty honest with you guys. Not pretty honest, I'm completely honest with you guys. And I was rushing to do episode 24, some of you may know. And later in the evening, when I came back and looked at it after it had been posted, I realized that I had made a little mathematical mistake in one little equation toward the end of the episode. And I probably should have just left it up and done one of those, I don't know, errata thingies that you can do in the description. I should have just done that. But I felt, look, I'll just fix it tomorrow. And tomorrow turned into episode 25, episode 26, and on it went. So I never got back to it. So bottom line, I am going to redo episode 24. Maybe, I hate to say promises that I don't keep. Maybe this weekend I'll find a little time to redo episode 24. Episode 24 was about Bohmian mechanics, de Broglie-Bohm mechanics. I don't know, maybe I could actually fold episode 24 into a longer episode where I talk about the various interpretations of quantum mechanics. Maybe that's what I should do. So I could do the many worlds interpretation. I could do the Feynman approach to quantum mechanics. I could do de Broglie-Bohm approach, as was the core of episode 24. And I could also do GRW theory, which is another approach to trying to make full sense of quantum mechanics. That would make for a longer episode, but that's okay. As you've noticed, I've been doing fewer episodes, but longer. So maybe that's what I should do. Interpretations of quantum mechanics, giving a little bit of the math of each, but maybe spending the bulk of the time on the Bohm-de Broglie theory. Yeah, I don't know. I think I may do. I kind of like that idea. So I think so. Abukar Faruqi, Professor Greene wants perfection in his work, smiley face. Yeah, well, we try for perfection. We never achieve it. But, if you see an error, it's a little hard. It kind of makes your heart hurt to leave that up. So that's why I fixed it, or didn't fix it. That's why I took it down. But we'll fix it. Joshua asks, hi, Professor Greene, Joshua Passa. Can we set the geodesic equation equal to the equations of motion to derive the metric tensor for that theory? Example given Maxwell's equation. Could we quantize the metric or not, like gravity? And it's a natural question. And anybody who studied quantum mechanics and then studies general relativity naturally wonders whether the means by which we quantize fields like Maxwell's field or the strong nuclear or the weak nuclear fields, could those techniques be applied to quantize the metric, which is the natural field in Einstein's theory of gravity? And the problem is when you try to do that in the most straightforward way, the quantization yields nonsensical results. That's the problem. We know how to go from classical electromagnetic theory to quantum mechanical electromagnetic theory. We know how to go from classical strong and weak nuclear force to quantum mechanical strong and weak nuclear force, and it all works, all holds together. It agrees with the observations. Spectacular. When you apply exactly the same template to the gravitational theory of Einstein, the result that you get falls apart. It's nonsense. When you do calculations in the most straightforward approach to quantizing gravity, the answer you get is infinity. And it's not like infinity should be interpreted as a highly likely probability. It's infinite probability. It's definitely going to happen. No, and infinite probability is nonsense. 100% probability, we know what that means. 101% probability, no idea. Infinite probability, nonsense. So that nonsense tells us that the standard approach to quantizing a system fails when it comes to gravity. So what have people done? Well, the loop quantum gravity people, they found a way to modify the standard quantization approach. They start with different degrees of freedom, not exactly the metric, something related to the metric. And this is somewhat controversial, but even the quantization approach that they use, some would say, differs in important ways from the standard quantization approach that any undergraduate learns in a quantum mechanics course. String theory takes a different tack. String theory says, look, let me just look at the quantum mechanical motion of a vibrating string, not even thinking about gravity. And lo and behold, when you look at the quantum mechanical vibrations of a string, you find in there Einstein's equations with modifications, but in certain contexts, those modifications would be small, leaving us with Einstein's equations. So in loop quantum gravity, you basically start with Einstein's equations and apply a quantization procedure to go from the classical theory to the quantum theory. In string theory, you start with a string, a classical string, you quantize it, and then you look at the kinds of forces that that vibrating string can transmit. And within there, you find the force of gravity. Miraculous. So it's a very different approach. And which is the right one? Nobody as of today can really say, because neither of these approaches has made contact in a specific way with observations. So Kawalajit asks, if strings are one-dimensional, then how do they vibrate in more than one dimension? And this is kind of fun because this is my third note to self that I should do an episode on string theory. I mean, it would be kind of weird to conclude your daily equation without having any mention of string theory in the more formal versions of the episodes. So just to refresh my own mind, I want to do one extra dimensions. I want to do one on string theory. I want to do one possibly on interpretation of quantum mechanics. So just to reiterate to myself. But back to your question, Kawalajit. When we say that a string is one-dimensional, what we mean is that if you were, say, an ant on that string, there'd only be one direction in which you could walk. You could go forward or backward, but there's only one independent direction in which you could move. But that is intrinsic to the string itself. The string can be embedded in a higher dimensional space. And therefore, the motion of the string can make use of all of the dimensions of the ambient environment, even though intrinsically along the string itself, there's only one dimension in which that ant could move. So that's the difference. You need to distinguish between the intrinsic dimension associated to an object, which is a dimension that spans the physical extent of the object itself. For the string, the span is only in one dimension, versus the ambient environment within which that object is embedded. And that ambient environment can have more dimensions than the object itself. This happens all the time, right? So you could have a flat piece of paper embedded in a three-dimensional world. And of course, the paper can ripple. Or a flag, right? A flag, if it's infinitely thin, it's got two dimensions on the surface of the flag. But you put that flag up a flagpole, the flag is embedded in three-dimensional space, and then the wind blows. The flag is moving, it's vibrating in the three-dimensional environment within which it is embedded, even though the flag itself only has two dimensions intrinsically on its surface. That is the difference between these two ideas. Okay. Siavesh asks, do you think AI will help us understand the universe or will it end us? Well, it could easily be both. I think I may have mentioned in the last episode, but I do get my live sessions and my non-live sessions and interviews and other conversations that I have sometimes mixed up. So sorry if I'm repeating myself, but not everybody who was at here now was at my other daily equation, say last time around. Um, so so there are AI researchers who came from the world of physics who are incredibly optimistic that we will use AI to solve problems in physics, that the patterns that we need to recognize in the external world and the mathematical embodiment of those patterns, we will find AI systems that are better able to spot those patterns and better able to find the mathematical framework for understanding them. So it hasn't happened yet, but when I listen to them speak, I do find it at least exciting and possibly even convincing that there's a really good shot that AI will assist us in taking the next step in perhaps the not too distant future. At the same time, that's not in contradiction with the possibility that AI, as you note in your question, could be the end of us. I mean, AI's goals need not align with human goals. I mean, we certainly hope that they will. We'll try to program things so that happens. But the whole point of general artificial intelligence is that there is a freedom and flexibility in the kinds of ideas and insights that run through the AI system. And who's to say that those ideas, insights, goals will align with ours? Moreover, how do we know that they won't be detrimental to us or ours? And, there have been doomsday scenarios that people have written down. I think I saw, I don't know where it was, you've probably seen it. Maybe it was a New Yorker cartoon or something, and maybe it wasn't even a cartoon, I don't know. But I saw this image where, you had some AI system that was charged with making more efficiently paper clips. And the cartooners who've probably seen it is, this system became so efficient at making paper clips that basically extracted all resources in the environment and filled the earth with paper clips, making it uninhabitable. So it was very effective at achieving its goal, not so effective at achieving or preserving our goals. So I can certainly imagine some catastrophe like that happening. Obviously, everybody will do all they can to avoid that. Okay, so Fabulous Ali asks, how was your experience on the set of The Big Bang Theory? A non-scientific question, sort of fun to answer those sometimes. It was great. It was great fun. It was a long time ago. It was when my next to last book came out. Yeah, so that must have been 2011. Oh my God, that long ago? I guess so. And I was on a book tour, and the producers of and the creators of Big Bang Theory, I don't know, they must have seen me on a book show or something, and they said, "Hey, would you like to do a book signing on national television on Big Bang Theory?" Because their idea was I'd be on the show, and Sheldon and is her name Amy? I always get mixed up with the glasses, the scientist counterpart to Sheldon. They would be at your book signing and riffing in the back of the bookstore. That was the conceit of the piece. So I said to them, well, let me think about whether I want to do a book talk, book signing on national television on the number one rated television. Let me think about, yes, I do want to do that. And so I went, and they had actually scripted it for me, but I said to them, I'm much better unscripted. I got the gist of where they wanted to go with Heisenberg and uncertainty. I said, look, let me just talk as I would at a real book signing. It'll be more natural, it'll be more real. And they said, fine. So I just sort of did that. And I just kind of talked at the front of the room, and Sheldon, and if her name is Amy, sorry, in the back. I mean, Maya's her real, no, what's her real name? Maim, I think so. I'm really, anyway. I need help when it comes to names, obviously. But anyway, so they were in the back of the bookstore set, chatting away and making wisecracks and jokes. And I tell you, so one funny thing, and then I'll move on back to science. Because of scheduling, we didn't shoot that in front of a studio audience. And everything they do when it was still on the air is shot in front of a studio audience. And they only use things that get a good laugh. So after this day of shooting, they said to me, we're going to show this segment tomorrow in front of our live studio audience, and we'll record them. And if they laugh, we'll keep it in the program. If they don't laugh, we won't. I was like, oh, goodness gracious. And thankfully they laughed. And so it was kept in the show, which is sort of fun. And it's also a funny thing from the perspective of, I've not done a lot of TV. I've done a fair bit of television. I had 7 hours of documentaries on Nova, Elegant Universe, Fabric of Cosmos. Had a 90-minute documentary last year, Light Falls, that I've mentioned here from time to time. And, I've been interviewed in a lot of shows and so forth over the years. But none of that has any impact compared to the impact of 90 seconds on Big Bang Theory. The number of times that people ask me about that dwarfs the number of times that people ask me about Elegant Universe and Fabric of the Cosmos at the end. So it's just interesting, the power of popular culture. All right, so moving on from there. I saw some kind of Columbia question, but I can't. It went by too fast, and I don't know where it went. Eric W says her name is Blossom. Blossom? I don't actually watch Big Bang Theory, but Blossom doesn't sound right. That's not who I have in mind. Blossom? Who's Blossom? Everyone's like, oh, he doesn't know who Blossom is. I don't know what you're talking about. Blossom. Now I'm talking about, she's like a scientist in the show. She's actually a scientist in real life. She has a PhD in neuroscience, I believe. But I can't remember. Is it not Amy? Someone tell me. Isn't that her name in the show? Can someone? I think it is. All right, I'm going to assume that it is. All right, so Abdullah TV says, I have a theory and I want to share it with you. Where can I do that? And how do I answer this question? And it is a good question to address. The number of theories that I'm sent is far greater than the number of theories that I can possibly look through in a lifetime. And it makes me feel bad because people work very hard on these ideas and they put their heart and soul into some of the papers that they write, but it is simply impossible for me to read through them. And I don't know what to say about that. I wish there was some way in which all the interesting theories that people in the general public come up with, that they could be vetted in some way. Maybe there's like some public crowdsourced website that we could create in which the various theories that people come up with could at least be looked at. I mean, how sad is it to work hard on something for years? I've gotten letters from people who've been working on theories for 20 or 25 years, and no one's ever looked at these theories. And they send them to me, often these thick stacks. And I look at them and I'm like, oh my God, this is going to take me like months to read through this. And I don't have great confidence. Maybe I don't want this to come off sounding wrong, but I don't have great confidence that with our present state of understanding, that someone can sort of leap to the frontier without having a full grounding in all the physics that came before. I think many people have in mind the image of Einstein in the patent office, the outsider. But bear in mind, Einstein had a PhD in physics. It wasn't that Einstein was just sort of some guy in the patent office. He was, number one, kind of the most brilliant scientific thinker the world has ever known, but put that to the side. But he had training. He had training in math. He had training in physics. He was therefore well equipped, especially at a time when insights into certain key ideas were in their infancy. But right now, maybe there are other ideas that would be in their infancy if we were to come up with them. But right now, general relativity is such a mature subject. Quantum mechanics is a mature subject. If you want to push the boundary of general relativity and quantum mechanics, you've got to know the state of the art in these subjects. And oftentimes what people are sending me is something that's meant to push quantum mechanics forward, push general relativity forward, push unification forward. And I look at the papers, and in the first paragraph, I don't recognize any of the things that we hold to be true. So that diminishes my confidence that that theory is actually going to be right. So the answer to your question, Abdullah, is I don't know. Don't send it to me. I mean, I don't mean to be mean, but if you send it to me, I know I'm not going to read it. So I don't want you to take the trouble to send it to me. But I wish in the best of all worlds, you send it to a journal, and the journal usually does make a quick assessment as to whether that paper will go into the review process. So that's certainly an option available to you. Or post it. I know there are these various physics, what are they called? Chat rooms? That's an old word. I don't know. There's a more modern word for it. Bulletin boards? No, there's some word, but you know what I'm saying. These places where people get together and discuss physics. Maybe there's somebody there who would take a look, but I apologize for just not having the time to go through everybody's theory. Maybe somebody has the answer and I'm missing it by not reading it. So that is the risk that I take. Okay. Um, what do we got here? Quantum Jumps from Austin, Texas. Questions, was your opinion of Columbia? I guess I'm partway through the question. I have to keep going. Columbia Professor Peter White's blog criticisms from Not Even Wrong. Look, I've known Peter White since I was a graduate student at Harvard. Yeah. Yeah, I went to give a talk at Stony Brook in 1987 or so. 1987, long time ago. And Peter White was a postdoc there, I think, and we met and we had great conversations. And I have, I think Peter is fundamentally a good person, and his heart is in the right place of trying to bring ideas to the public to try to minimize the hype that sometimes does happen out there in the world. I mean, I think sometimes he's probably accused me of hype, and that actually strikes me in a deep place. I mean, you gain a thick skin after a while when you're out there in public in, at one level or another. But I do all I can really not to hype the public. I really do. I'm very sensitive to qualifying radical sounding statements. When I talk about the multiverse, inevitably I say these are hypothetical ideas that emerge from the mathematics. We don't know if these ideas are correct. When string theory, when I talk about it, I inevitably emphasize that we don't know if these theories are correct because we haven't connected them with observation and experiment. So, and I don't do that for Peter. I do it for me. I do it because it's part of my DNA that I want to be out there speaking in a way that people can trust. I've turned down being on major television interview programs because the topic wasn't something I felt I had any expertise in, and I don't want to be out there just spouting hot air. So I think it's important to have someone policing, if you will, or indicating when science is described with unnecessary hyperbole, unnecessary hype, if you will. So I get it, and I think that's fine and it's good. I do think that Peter becomes unnecessarily negative sometimes on ideas at the forefront that we know are speculative, but nevertheless, the mathematics is to us so interesting and compelling that we're willing to spend some time on it. So, I think what he's doing is fine, and if people enjoy it and learn something from his blog, fantastic. If people get excited about science and it reorients their thinking about what aspects of recent work are worthy of attention and which aren't, fine. But I do think you need to listen to a spectrum of people, a spectrum of people that you can trust. And I hope that these sessions have given you confidence that I'm one of those trustworthy individuals who really does put effort in to giving answers that are sufficiently qualified and sufficiently aware of the ways in which other outlets may promote unnecessarily certain far out ideas that really don't hold any water. I mean, that's why, for instance, in the last one of these live sessions, I think I began by talking about these headlines, talking about NASA finds evidence of a parallel universe in which time elapses in the reverse direction. It's like, oh my God, really? Again, it's not that that isn't an idea that was put forward by some scientists, but it's put forward as just one of a collection of ideas, many of which are much less far out. And I think it's unlikely that that far out explanation will explain the data of the cosmic rays being found in Antarctica. So it's unfortunate that those kind of over the top suggestions, which are put forward by well meaning scientists, no one's trying to mislead the public. That's not our goal. But in the hands of journalists, sometimes things get hyped in a way that can be misleading. So anything that helps pull that back ultimately, I think, is a good thing. Okay. Danny L. McCawy asks, does the fact that a scientific theory makes correct predictions necessarily mean it is true? Would it be accurate to say that Newtonian physics is false but still makes good predictions? So to the first question, no, whoa, John, sorry about that. I almost knocked over my microphone. It is not the case that a theory that has a history of making highly accurate predictions is necessarily true by any means, right? I mean, a theory can make accurate predictions for experiments number 1 through experiment a million. And then on experiment 1,000,001, all of a sudden you're like, we have a crack in the foundation. The prediction of our tested theory is disagreeing with observation. So all theories are provisional, right? It's virtually impossible to prove a theory. All you can ever do is increase your confidence in the veracity, the truthfulness, the relevance of that theory by testing it in as many distinct contexts as you can. And so, Newton's theory was tested in a great many experiments between the late 1600s and, say, the early 1900s, and it worked. But then Einstein revealed that if you would have tested Newton's theory in environments, where the speeds involved were enormous, it would not work. And the special theory of relativity supplanted Newton's in that case. But exactly as you're saying, Danny, we still use Newton's theory from a practical standpoint. If you want to calculate the trajectory of a baseball flying from home plate to the outfield, if you want to calculate the trajectory of a rocket going to the moon, the Newtonian description is so fantastically accurate, even if it has been superseded by the quantum mechanical and the Einsteinian view of the world. Those theories only yield the most modest modification to the Newtonian prediction in everyday situations. And so it is accurate to say that Newtonian physics is in some sense false, but still makes good predictions. In fact, the way I really like to say it is not exactly in that language. I like to say that Newtonian physics is accurate in a certain domain of the world, when things are not moving too quickly, not near the speed of light, and when their masses are not so large that the general theory of relativity comes into the picture. And so if you want to enlarge the domain and allow yourself to consider very high speeds, you better shift your theoretical framework to special relativity. If you want to enlarge that even more to allow for aggregates of matter where the force of gravity is really strong, like black holes, you need to enlarge your framework to include the general theory of relativity. So that's really the way science progresses. You have a theory that works in some domain of reality, and when you want to expand that domain, you need a new theory. And when you want to expand that domain, you need a new theory still. Will that ever stop? Will we ever have a theory that just works in any domain that you could possibly imagine? Maybe. Maybe that is string theory. It could be. Maybe not. Again, we don't know if the theory is right. It hasn't made contact with observation or experiment in a way that allows us to adjudicate, to distinguish it in a manner where we can say, that's the theory. that's describing the world. But that is the way physics progresses. Okay. Um, let's see. What else do we have here? Actually, what time is it? Oh, it's 4:45. All right. Let's just answer a few more questions today. Um, so this is a question that seems to come up on occasion. Maybe Mr. Castle asked it last week. I don't remember things well enough. But are brain thoughts quantum processes? So if Mr. Castle is asking this a second time, sorry for answering it a second time, but at least I'll remember for the third time. Um, so are brain thoughts quantum processes? Of course, they're quantum processes. Are they due to the physical motion of the particles? Are they due to the physical development of the fields that are existing within the architecture of the brain? Absolutely. I don't think that consciousness and thoughts are anything more than that. Are the mathematical description of the forces at play for the motion of particles and fields, regardless of it's a brain or a piece of Swiss cheese, are those laws quantum mechanical? Of course they are. So, in that sense, I would say the answer is both yes and no. I don't think, and I could be wrong on this, maybe future discoveries will reveal some iconic quantum quality that is the essence of consciousness. Maybe. But without that, I would say that a brain involves processes internally that are quantum mechanical, and a block of Swiss cheese involves internal processes that are quantum mechanical because everything is quantum mechanical. The real question is there some iconic feature of quantum mechanics, like quantum entanglement or something like that, that's at the essence of physical processes feeling the way they do to us human beings, feeling like grief or joy or excitement or boredom, as the case may be. And that's a question that I can't answer. My suspicion is that it's not intrinsically quantum mechanical in some fundamental way that distinguishes the processes inside a brain from those of a block of Swiss cheese. But we will see going forward if that perspective continues to be viable. Maddie M says the best theories are those we can quickly disprove. They allow us to learn and move on. Well, yeah, sure. In the best of all worlds, in the best of all worlds, excuse me, in the best of all worlds, you're right, Maddie. If every time we came up with an interesting idea, we could put it out there and there was a machine that could just test it, disprove it, say, allowing us to throw that away and move on, that would be the best. And frankly, if we could do that today with string theory, if we could find any means of proving string theory wrong, I would be thrilled to bits. And I'm not joking when I say that. I'm not wedded to string theory. I've enjoyed working on it. The math has been incredibly exciting. The math has forced me to learn and expand my own knowledge in what for me have been gratifying ways. I've been fortunate on occasion to work on questions that were ready to be cracked and was able to contribute insights that people found valuable. That always makes you feel good. But I'm not wedded to any particular theory. I am enamored with the possibility that our generation will take us one step closer to the truth. But there are many ways to take that one step. And as you point out, Maddie, one way is to rule out theories that are wrong, because then it focuses your attention, hopefully, on theories that have a chance of being right. But the thing that you need to bear in mind, Maddie, is just because a theory is so rich and complex. And just because a theory shows its true colors in domains that are so small or so energetic that they're beyond the reach of today's equipment, that shouldn't be taken as a black mark against that theory. No. It should be taken as a recognition of the state of play. And so, because string theory is difficult to test, because it does really reveal itself on a short distance scales and high energies that are beyond the reach of at least today's equipment, that's not a reason to say that the theory is not worthwhile. It's simply a reason to recognize that it's going to be hard to come to a determination of whether string theory is right and wrong. And notwithstanding people like Peter White saying that string theory qualifies for Wolfgang Pauli's statement, not even wrong, that to me feels very counterproductive. That kind of harping from the sidelines feels very counterproductive to me. If it was me harping from the sidelines on string theory, I'd rather be spending my time trying to prove string theory wrong, or maybe even trying to prove it right, or trying to contribute something to the theory, or trying to take a different direction entirely and say, aha, this is the way to quantum gravity. To simply say that a theory like string theory is not even wrong is so unnecessarily negative. It doesn't accomplish anything, because we who are in the forefront of string theory itself, we readily say that this theory is hard to test, that we've yet to test it, we've yet to find direct observational signature of the theory. And we keep that in the forefront of our thinking because it keeps us on the lookout for indirect ways that we might make contact between string theory and observation. So you don't throw away a theory because it takes a while for it to be tested. That's just, I would say, not a good means of adjudicating between worthwhile theories and theories that are not worthwhile. Yeah, so Jacob Booner said, yes, that is Pauli's phrase. It absolutely is Pauli's phrase. And, Pauli was a famously caustic physicist who had a very sharp intellect, sharp insight. And look, if you take it in good fun, if you take not even wrong in good fun, sure. Yeah, that's the way things are at the moment. We just don't know. But I would say that many theories in the stage of development, I'd almost say that every theory in the stage of development, if you're pushing the frontier of understanding, then you are in a domain of not knowing whether your theory is right or wrong. And that domain of development can stretch on for decades. If a theory is sufficiently rich and interesting, that progress can be made even though the theory is yet to be tested. So that is just the way things are currently with string theory. Yeah, so Quantum Jump says it's easy to criticize, it's difficult to provide an alternative. And I agree. That's a quicker way of saying what I was saying just a moment ago. If you're going to spend time and effort criticizing a theory, that's one way. Look, life is short. Life is short. So you have to ask yourself, why would someone spend their time criticizing a theory as opposed to spending their time trying to develop a theory? How much more exciting, how much more useful, how much more impactful to come up with new, real ideas that push the frontier of understanding forward, as opposed to standing on the sideline and saying, nah, People make their own choices how to spend their time. I have an outlook. I like to think that I'm optimistic and positive. And certainly I spend my time trying to push understanding forward, trying to bring understanding to a wide audience that might allow others in the group to push understanding forward. And to me, it's just so much more exciting. Your life is more exciting when you're developing new ideas than when you're sitting on the sidelines writing a blog that's critical. I don't know. To each his own. Paul C., your book really is good, by the way. Thank you. I appreciate that. So SI Monster from last week was asking what is gauge symmetry, and I think I promised. Oh goodness, I promised I'd answer what is gauge symmetry this week, and I don't feel I'm prepared to give a good answer to that. I know I promise for next week, SI Monster. I'm gonna start. It's a hard question. What is gauge symmetry? Let me just point out in the Elegant Universe, in chapter, it must be chapter 7, I think. I take on gauge symmetry. I tried to describe it in general terms. I'll go back and reread what I wrote there 20 years ago. It was hard then. It's just as hard now, but let me just try to come up with something that will satisfy you. SI Monster. I apologize. Okay. What do we got? I haven't looked over at the Twitter stuff in a while. Let's see what we got here. Let's see. Anything that strikes me? So Morgan Waxland asks if time moves differently relative to mass. Well, I think that means if mass itself can impact the passage of time, which it does, and the universe can have more mass here or there at a different moment in time, could our perception of time be skewed because of that? And the answer is absolutely yes. If a civilization was born and existed hovering inside a ship at the edge of a black hole, then time as it elapses for those individuals would be quite different from time as it elapses for us. So, as we look at them, we would say their clocks are ticking off much slower than our clocks in this environment here on Earth, far away from, say, that black hole. And therefore, their perception of the universe would be skewed in the temporal aspect by virtue of the environment that they inhabit. Now, you might say then, okay, then like who's right? And I'd say, well, no one's really right. It's just that time is not universal in the way that Newton described it. Time is very much, I hate to say it, sounds hackneyed, it's in the eye of the beholder in the sense that time elapses at different rates for different observers moving in different ways. And in the question of Morgan, experiencing different gravitational fields. So, what makes us think that there's any sense to a statement like the universe is 13.8 billion years old? What does that mean? if in different environments with different amounts of mass, perhaps even different motion, clocks tick off time at different rates, what do we mean by this seemingly universal cosmic statement about the age of the universe? And the answer to that is this: we live in a very special universe. We live in a universe which is highly homogeneous and highly isotropic, not isotropic, isotropic. What I mean by that is that, let me just talk loosely. If you take a chunk of the universe, I don't know, it's got to be pretty big. Call it 100 million light years across, like a big chunk of the universe. Every 100 million light year chunk of the universe, if you average out over the mass, and if you average out over the variations in temperature and so forth, if you average all those physical qualities in that big chunk of the universe, then every 100 million light year chunk of the universe is basically the same as every other 100 million light year chunk of the universe. That's what I mean by homogeneous. You know, the example that I use, oh, I don't have my murky Earl Grey water here any longer. But you know, you think of a cup of coffee, macroscopically, it looks like a uniform brown liquid. Let's say you've got some milk in there, uniform brown liquid. But you know, if you dive into the coffee and you examine it on sufficiently small scales, it's not homogeneous on small scales. water over here, milk molecule over here, sugar molecule over here, whatever. It's got all sorts of stuff all over the place. It's only when you average out over the entire cup of coffee that it looks like uniform brown sludge. Similarly, the universe certainly has differences from place to place. You could be near a black hole, or you could be near a planet, or you could be in emptiness of space. But if you average all of the matter in a big enough chunk and average out all of the temperature in a big enough chunk, then, like the coffee, which looks like uniform brown sludge, the universe looks like uniform physical properties. And so, if you use a clock that is sensitive to those average uniform properties in a given 100 million light year chunk of the universe, then all clocks of that sort will have experienced more or less the same physical environment and conditions and evolution since the Big Bang. And that's the kind of clock that we use when we talk about, say, a universal notion like the age of the universe. So, yes, at the level of the individual, the matter in your environment can absolutely skew your temporal perspective on reality. But we, in order to remove that very individualistic quality of time, when we talk about cosmic time, we're talking about time measured on clocks sensitive to the overall average features of the physical universe. And because the universe is homogeneous, those physical features from place to place on average are more or less the same. Therefore, clocks take off time at more or less the same rate. Important, very important idea, very important question. All right. What do we got? So it's 5 o'clock, guys. Should we wrap it up for today? I'm starting to feel a little bit exhausted and hungry myself, but let me just see if there are any other questions that catch my eye before we do that. Well, Ian Richard Gradwell asks, maybe we perceive one linear hour of time because we perceive only 3 dimensions of space plus 1 of time. What would happen to our perception of motion and trajectories and so on if we were perceiving not just 3, but 5 or more dimensions? And if, so Ian, my answer to that question is, if we had more space dimensions that we were sensitive to, I don't think that that would give us much insight into the arrow of time. In a universe that has a plurality of spatial dimensions like 3, that doesn't give us any particular insight into the arrow of time. And so if we had 1 more dimension of space or 2 more, whatever, I don't think that the insight that we would gain from picturing reality with those extra dimensions would really help us at all with the arrow of time. Others have suggested something similar to what you suggest, Ian, though, which is even yet more radical. People have suggested maybe if there are more than one dimension, if there is more than one dimension of time, if there are 2 dimensions of time, could there be some kind of symmetry between past and future among these multiple time dimensions? And I don't know. People have tried to work out the mathematics of a multi-time universe. It seems as though in some versions you can make some sense of a universe with 2 dimensions of time. It's never really caught the physics world by storm. So nothing that I've ever seen has provided me an aha moment from imagining a world with more than one time dimension. But who knows, maybe in the future someone will develop something in there that is insightful, but I've never seen it, at least not as of today. um so Andre Veltman says, enjoying your equations in the Netherlands daily, almost daily. They were daily for a while. Now I think it's more like 2 or 3 a week, including this live session. I think it's probably the rhythm that we will get into. I think I will try to have one for Monday, and I think I will focus on extra dimensions since a lot of people are asking about that. But Andre Veltman asks, how can a quantum bit be of any use? In spite of my PhD in electrical engineering, I fail to understand the details. And well, I don't know if my answer is going to help, Andre. It's probably a description that you've heard in one form or another, but I'll say it anyway, just in case it is useful to you or to anybody else listening. We all know that computers are based on an architecture in which you have bits, binary digits that can be 0 or 1, plus or minus, whatever. And that's a very computationally useful way of breaking down interesting questions, interesting problems, to frame them in terms that only require us to process zeros or ones that are moving through various integrated circuits. And the idea of a quantum bit, a qubit, is to make use of the fact that in quantum mechanics, sure, you can have, say, spin up or spin down, that's like a 0 or a 1, but the quantum mechanical wave function allows for the weirdness of superposing an up and a down. And you can't really think about that as going off at a diagonal. Pictorially, I guess you can. But it's really that we can have a bit that simultaneously has a little part of 0 and a little part of 1 simultaneously. So in some sense, if you have a collection of qubits, you're able to do a whole variety of computations simultaneously, because those qubits can embody both the 0 state and the 1 state simultaneously. And if you want to think in what I would say is unnecessarily speculative language, but I think it's useful, and some of my colleagues do not think this is speculative at all. They think this is how quantum mechanics works. But if you use the so-called many worlds interpretation of quantum mechanics, where when something is a mixture of up and down, and you go about engaging with it, interacting with it, according to this view of the world, what happens is there's a universe in which it is up and a universe in which it is down. So these are not just hypothetical blendings of mutually incompatible realities. It's an actual blending of what we would normally in classical language describe as mutually incompatible realities. How can something be up and down simultaneously? How can something be a 0 and a 1 simultaneously? But if you allow for the quantum flexibility that allows for a blending of up and down or 0 and 1, and if you interpret that in the many worlds interpretation, then in some sense, when you're doing a calculation with qubits, you're making use of a huge number of parallel universes to carry out the calculations for when, say, the first bit is up and the second bit is up, or a different universe when the first bit is up but the second bit is down, and so on. So you're using the quantum flexibility of qubits, in some sense, their ability, if you think this way, to access many worlds simultaneously, to use the computational power of many universes to exponentially speed up the duration for a given calculation. And that's what a quantum computer promises us. Now, again, in the spirit of not overhyping things, although some would say I'm about to underhype quantum computing, we know that there are certain kinds of problems that are amenable to algorithms that will leverage the computational power of a quantum computer. But it's not like every problem, every question that we've ever asked, we know how to frame it in a way that will truly make use of the power of quantum computation. And so it's not like once we have quantum computers, every calculation speeds up exponentially. That's not guaranteed by any means. The only thing that we're certain about is that those computations for which we have already developed a quantum algorithm for enacting that computation, then those will be sped up enormously. But it could be the case that there are a limited number of problems for which quantum computers will give you that kick. And maybe these are the most important questions, the ones of most interest, whatever. So I'm not going to value judge it. But it's just to say that don't immediately think that quantum computation universally speeds up all calculations exponentially. That requires finding the algorithms that will do that. Well, I've got an interesting, do you see this beam of light that's kind of going through my head right now? Wow. kind of dramatic. What does that mean? Is that the alien ship, the UFO, beaming in, I should say, on our conversation, trying to distract us? I think not. But there it is, Area 51, shining, a ray of light through the Catskill Mountains in New York. Well, I like this one. Alice Vache asks, Sir, have you any life advice to offer us? I have no doubt you have much wisdom to offer. Many thanks, Alice. Well, I like to think that I've got some advice. I don't know if it's great wisdom, but I certainly to young scientists, I would say that the most important thing at an early stage is not to be at the frontier of knowledge. The most important thing is not to spend 3 hours talking with me about critical questions at the forefront of string theory or quantum mechanics. The most important thing is to learn the basics inside out. And sure, you can spare 3 hours a week to do something like this. That's really not what I was meaning, as the number of people listening dropped off by 50% when I said that. Um, what I really mean is that it's so important that you learn the groundwork that one day you will use if you go on in science, because nothing is more valuable than the foundation upon which you can build insights at the forefront. But without the foundation, you will constantly find yourself collapsing through rotted floorboards, unstable joists in your understanding. And it's best to get that solid now at the learning stage, not try to fill that in later on. I guess advice number two I would give was someone gave me a long time ago. When you come to do your PhD, those of you a little more advanced, I would say don't view your PhD as the best work of your life. View your PhD as an important stepping stone to get you into the community of researchers, to get you out of school and into the realm of full-time research. Because there are many people who spend an inordinate amount of time on their PhD thinking that this is a defining moment in their career. It's not for most people. I mean, for a few it is, but for most people, their PhD is a necessary step en route to the important discovery that they will subsequently make. Again, there are exceptions to all of this, but I wouldn't allow an unnecessary focus on achievement in your PhD to slow you down. Get it done. Get the PhD done. Get out into the world, get a postdoc job, get into full-time research, focus your attention fully at that point, and don't spend 10 years getting that PhD. Don't spend 8 years getting that PhD. 6, okay. Don't go more than 6. 5, that's even better. 4, better still. Approach I took, got done 2 years. 2 years. I just wanted to get it done. And then I was out in the world doing stuff. So that would be one piece of advice. Again, Alice, I'm not sure which side of the academic or not academic world you approach that question from, but at least for the academic side of things, those are pieces of advice that I do feel strongly about because A, they help me, and B, I've seen them in action so many times. So Sai wants me to be the PhD advisor to his or her or their PhD thesis. Maybe. Got to come to Columbia though for that. Where'd that question go? I got to keep my fingers off of this thing. Randy Lamunda says maybe great life advice could be to find some talented physics student and fund them. Well, yeah, I mean funding. I mean you end it with LLL, but yeah, I mean funding is a big deal, and it's become ever more difficult. You know, the Department of Energy, for instance, is cutting funding in subsequent years with all that's going on in the world. And the funding directly affects the number of students that we can support, the number of PhDs that will be granted. the number of new, able, smart, energetic physicists that will enter the field. So rather than looking to government, I think we may, at least in the United States, need to look to philanthropy. Think about the people who got trained in physics and went on, or mathematics, and went on to make billions of dollars. A great example is Jim Simons, as you may know, who incredibly successful in the financial world, who was a mathematics professor before he made that move into finance. And now he's using his money to do the most wonderful things, supporting postdoctoral fellows around the country, supporting, for instance, the World Science Festival. Vital, the support that the Simons Foundation, Jim and Marilyn Simons, provide. Also providing support for faculty who are going on leave to pursue research. So the more people who would do that, the better off the field would be. So that is actually a vital part of, from a student perspective, of what the future will be like. So Joel Jarvinen asks, "Hi Brian, thanks for the PhD advice. You're welcome. Going to keep that in mind. I hope you do. Anyway, could you elaborate on the concept of speed in time? What unit do we use? Seconds per what?" Yeah, exactly. So what I really have in mind when I talk about speed through time is the more general idea of speed through space-time. And you may know, again, I'm not sure what your background is, but in the special theory of relativity, there is a natural notion of speed through space-time that comes from the 4 vector dx alpha d tau. And that 4 vector has a length in the Minkowski metric that is a magnitude equal to 1. So when I talk, and 1 is where the speed of light is equal to 1. So when I talk about speed through space-time being 1, in equations, that's really what I have in mind, that dx alpha d tau contracted with dx alpha d tau with the Minkowski metric eta alpha beta gives you a number whose magnitude is equal to 1. What do I mean in more general language? The more general language is that when you're sitting still, you are not moving through space, but you do have motion through time. And you really can think about that, if you want, as 1 second per second. You might say, well, that's kind of a silly idea, but it's not that silly when you think about it, because if you allow for that notion of 1 second per second, then when you start getting up to move, the rate of ticking on your clock, from my perspective, won't be 1 second per second. It'll be a number that's less than 1 second per second, because I see your clock ticking off time slowly. So what I'm really talking about is, it's the rate of your motion through time compared to the rate of my motion through time. And when we are mutually at rest, then our passage through time is the same, 1 second per second. But as you get up and start to move through space, your speed through time slows, in the sense that the ticking of your clock is less than 1 second per second. As I'm watching it go tick-tock, and I'm watching mine go tick-tock, yours is tick-tocking less frequently than mine. And that's the sense in which I can say your speed through time is 0.7 seconds per second, or 1/2 a second per second. Your clock is only ticking 1/2 a second, while mine is ticking off time 1 second. So it's a very concrete operational definition of your speed through time. It's the measure of your passage through time compared to my passage through time. Okay, so ETEM79 says, my video and my sound are not in sync anymore. That is a relativistic effect that happens when my thoughts are near the speed of light. There is a disjuncture between my visual and my audio when my thoughts are that fast. So I will try to slow my thoughts down to try to bring synchronization between my audio and my video. I think I may have accomplished it by now, but it could also be an internet slowdown. Okay, so Joel gets back. Oh, I see. Thank you. That clears things up a lot, actually. Great. I'm glad. In fact, I'd love to hear a little bit of feedback so I know whether what I'm saying is getting across at all. Oh, it is in sync for Thomas and others. Good. All right. I'm glad to hear that. All right, maybe one or two more questions and then we will call it a Friday day out here, which those of you, I mean, how many of you is it like early morning? Anybody, it's like 2 o'clock in the morning or something? I know that occurs for some of the regulars on this. Yeah, so Koala Jeet wants to know about our general relativity course. I don't know. I'd love to create a general relativity course for World Science U, but it's so time consuming to create. But I was thinking maybe this is a way to think about it. Koala Jeet, maybe instead of putting out a full general relativity course, maybe I just set as a goal to get out like the first 5 modules of a general relativity course, put that out there, and then sometime later do the next modules. I don't know. Maybe I can break one course up into 10 courses and do parts 1 through part 10. Maybe that will be less intimidating. So it's almost 3 a.m. for Arjan. It's 11 p.m. in Sweden. Joel, where are you in Sweden? I have a warm spot for Sweden. Quantum jumps. Can't wait for a talk on dimensions. What math will you use? Oh, well, I'm not going to do heavy duty math. I was thinking of just doing an explanation of, the very basic distinction between 0, 1, 2, 3, and 4 dimensions, just using hypercubes, tesseracts as the operative example. That's sort of what I had in mind. And I also, we have a VR project. I don't know how many of you have VR equipment at home or have access to VR equipment. I don't know if you have that. I wouldn't mind hearing you just sort of note it in the chat, because we have this VR lecture that we're developing. We did it once, but now we're redeveloping it even in a more refined way, in which if you have VR equipment, I think you need an HTC Vive or something like that. Using that, you'll be able to join me in a futuristic lecture theater floating in outer space, and I'll explain the basics idea of string theory in that VR environment. And we will also be able to build in virtual reality tesseracts, hypercubes in 4, 5, or 6 dimensions. So if you have the equipment, that is the coolest way to experience some of these ideas. So I'll maybe in the link for your daily equation, when I talk about the extra dimensions, I'll have a sign up place for those of you who happen to have the equipment or access to it, so you can join in on that. And that's sort of the best way to experience this stuff. But I don't intend to really do higher dimensional Riemannian curvature and things like that. I think it'll just take us too much into the technical details of higher dimensional spaces that won't be as interesting to the people who typically watch your daily equation. Murad Ozel just asked one little question toward the end here. Is there a God? I don't know, Murad. What do you think? All I can say is that if there is a God, God's been doing a pretty good job of staying behind the scenes. Recently, God's been doing a pretty good job of allowing lunacy to hold sway in America. It's the old problem of evil that the philosophers debated across the ages. If there is a good, all-loving God, why is there evil in the world? And, there are many answers. I'm sure you're familiar with them. The idea that God creates some life form and then allows that life form autonomy. And only by allowing that life form autonomy can the good acts of that life form really have meaning. But the capacity to do good comes with it the capacity to do evil. I don't know. I'm not really all convinced by this kind of stuff. But if you ask me my gut feeling is sure. There could be a God behind it all. set it all in motion, and all we're doing is figuring out God's handiwork. Possible. I don't see any evidence for that whatsoever, but that doesn't mean it's not true. On the other hand, if all that we physicists are doing is working out the underlying laws and there is no God, and what we're figuring out are the mathematical patterns that govern reality, if that's what we're doing, not revealing God's handiwork, but just revealing the patterns that for some reason are woven into the texture of reality, I'm quite excited to be part of either of those journeys. If what we're doing is revealing the truth that God put into place, wow, what a noble way to spend your time. If what we're doing is just working out the patterns articulated in the human language of mathematics, wow, what a noble way to spend your time. So, in a real concrete sense, it doesn't affect my day to day work, whether there is a God behind it all. But for other questions, for many people, questions of value and meaning are intimately connected with the potential existence of a God. From my own perspective, I like to flip it around a little bit. I don't view the journey toward those insights that for some people, not all, but for some people that religion helps reveal. I consider those journeys not to understand the external reality, but rather to understand the internal reality of conscious awareness, the internal subjectivity of what it means to be a life form, a human being living in this universe. And that journey to understand our own conscious awareness, to try to understand why we behave the way that we do, why we have the feelings that we do, to try to understand the truths that are not amenable to description in ordinary language, the kinds of truths that would be diminished by trying to describe them in ordinary language, the truths that we can sense and feel, but we can't quite articulate. For some people, that's what the spiritual journey is all about. And I consider that to be a valuable journey. I consider that to be a complementary journey to the one that we physicists try to reveal in the equations describing an objective world. So that doesn't necessarily mean that the journey is toward a God in any conventional sense, one of the dominant world religions. Rather, I see it as a spiritual journey that recognizes that there's more to the world than the objective truths that are available to everybody who studies the universe with adequate intensity. The subjective truths that are only true for you or only true for me, those are not available to everybody. They're only available to the individual. And you can do your best to explain them if you want, if you're motivated, but ultimately they are deeply personal qualities of your peculiar combination of particles that defines you as an individual being in this reality. And I think that the journey to understand yourself in that way is a valuable one. And I consider that spiritual. Some would say it's religious, but clearly the language and the approach that I'm describing is not fully aligned with any of the more conventional world religions. So it's oblique to perhaps what you had in mind, Murat, when you asked, is there a God? But nevertheless, I hope that gives a sense of how I organize my own thinking about the qualities of the world that matter. All right. So Robert G. Gnome says, I think it is a bad idea to call subjective stuff, quote, someone's truth. Plenty of good names for those things. And I'd be interested to know what you mean by that, Robert Genome, because I really am using that language with forethought. And it, for me at least, it does capture in language as best as I'm able to the ideas that I'm trying to communicate, which is there really are to me qualities of the world, qualities of being alive that are deeply personal and deeply iconic. It's not that others don't have similar feelings. That's not what I'm trying to say. But they're not things that I need to be verified through observation or experiment. They're not things that I need to have a mathematical equation in order to feel that I've grasped. When I'm listening to a great piece of music, the Goldberg variations, Goldberg variation number 25. Wow. When you listen to Glenn Gould's version of Goldberg variation number 25, and the feelings that can inspire, I don't know the words to describe them, but I can't help but describe them with the word truth. And I can't help but put the word subjective in front of it, because I know it's a truth that's emerging not from some objective analysis of, say, the electron's magnetic moment, but rather a subjective feeling that I don't even care if I'm able to describe to the objective world with any degree of accuracy. I know it's true. I can feel it. It's a quality of the world that I deeply value. And therefore, I tend to use the language subjective truth to describe it. So if you have other language that you think is better and works better for you, by all means, use it. Really, I mean that. But for me, I have found that notion of subjective truth to be a useful one. Now, I do agree that you can take these notions and twist them in dangerous ways. You can start to twist them and talk about alternative facts. You can say, well, that's a fact that's true for me, but not for you. That's not what I'm talking about. I'm not talking about qualities of the world that are accessible to all of us. I'm not talking about what happened in a conversation between one leader and another. I'm not talking about whether the climate is undergoing certain transformations. I'm not talking about the objective qualities of the world that in principle are available to all of us if we are privy to the information and if we are privy to the equipment necessary to become aware of that information. I'm talking about the deeply personal qualities of existence. And there is a pretty clear way to have a demarcation between my use of the word subjective truth and the ridiculous, the dangerous, the unjustifiable, the devious use of terms like alternate facts. No connection whatsoever. Yeah, so the Chopin Funeral March, I agree. There are many, there are many ways to achieve the kind of experience that I was referring to. Robergino, and by the way, I got into string theory research with the Elegant Universe. Thank you so much for that. So yes, no, I wasn't trying. I hope my little diatribe here was not taken as a critique of what you said at all. I'm just giving you my honest reaction to the comments that I'm reading here. So Brad Dibble, hi Professor Greene, Louisville Slugger here, by which I suspect Brad is reminding me that he has spoken of the Louisville Slugger that I see currently in the corner of this room. How do physicists know that the CMB started 380,000 years after the Big Bang? And the answer to that is we have an understanding of how the universe changed in time coming from the equations of the general theory of relativity. We have an understanding of the temperatures at which, say, electrons will be so juiced by the ambient temperature that they will not stick in orbit around protons. And it's when electrons are able to stick in orbit around protons that the material in the universe becomes overall neutral, positive proton, negative electron. High enough temperatures, they're all floating this way and that. And when they're floating this way and that, light can't penetrate. Why? Light is affected by the electromagnetic force. Light is the carrier of the electromagnetic force. If you've got charged particles around, the light gets buffeted to and fro, and it can't get through the plasma of particles. It becomes opaque. Only when the protons grab the electrons, making neutral atoms, can light freely travel, because now it's not encountering the charged particles of the plasma. And we can work out how long it takes for the universe to cool down after the Big Bang for that so-called recombination, that putting together of electrons and protons into neutral atoms, how long it will take. And it will take about 380,000 years for the universe to settle down into a state where there isn't a plasma of charged particles that prevents the cosmic microwave background photons from traversing through space unimpeded. And that's where that number comes from. The other thing it comes from is we can measure the degree of redshift. This came up earlier, the degree of redshift of photons. And the degree of the redshift of the photons gives us an understanding of how long they've been traveling. Together with our cosmological theories, we can figure out how long they've been traveling. So that's where these numbers come from. So Soban, I don't think I'm pronouncing that right. Soban Rabbani. Last night I was watching the episode you talked about, the Big Bang with Dr. Tyson, Neil Tyson, on a Star Talk show. Absolutely fantastic. Thank you. I was amazed by the effort you put on string theory, all these. Oh, okay. That was just a compliment, not a question. So thank you, Soban. I appreciate that. All right. Anything left to go? Any time left? Oh, it's 5:30. So I don't know. Maybe we'll go for a few more minutes and then wrap it up. Okay. Well, life and thought always exist in the universe, and is cyclical in the universe, cyclical, infinite. Well, look, if the universe is cyclic, expands and contracts, then our universe is one episode in that sequence. And we have no idea whether life is a natural outcome or a rare outcome. And therefore, we have no idea whether life will persist in the other cycles. We just don't know. It's possible. You know, there's interesting work by Jeremy England and collaborators. In fact, Jeremy's coming out with a book. I'm meant to read it. I've got to read it really soon. I want to give it it seems like a wonderful book, so I want to endorse it. But I have to finish the reading of it. But Jeremy has these theories, or a theory about life, that perhaps suggests that life might be a fairly commonplace outcome of a hot star raining down energy on a planet with certain kinds of complex molecules. And, you know, if that's the case, then maybe life is commonplace, and maybe indeed life would be commonplace across all the cycles in a cyclical cosmology. But there's nothing that establishes that as an absolute truth. So who knows? Maybe if you had a cyclical universe, maybe none of the cycles except ours would support life. Possible. Just don't know. All right, I'm going to look for a final question here and then wrap it up. All right, I'm gonna end with shortcut. Will psychedelics help us understand consciousness? I think the answer to that is yes. And I'll tell you why. You know, one of the most difficult things about understanding consciousness is that we try to understand consciousness with consciousness. We try to understand the phenomenon by experiencing the phenomenon. That's not to say that careful researchers, don't do everything that they can to try to find objective signatures of conscious awareness. And they look for correlations within the physical properties of the brain, the physical processes in the brain. They try to line up certain kinds of qualities of conscious experience with certain kind of physical processes taking place in the brain. So all of this is great, but you can't help but wonder, about the possibility that if our experience of consciousness is much broader than it would be in the absence of psychedelic experiences, that can't help but broaden our perspective on what consciousness is and what it's capable of and what the phenomenon that we're trying to explain, what they actually are. And look, this is a slippery slope and a dangerous path to walk down because not all psychedelic experiences are benign. Not all of them are safe. So these kinds of explorations need to be done in as safe a way and as a controlled a way as possible. But I am of the opinion that broadly broadening our understanding of the spectrum of conscious experience can only help to provide insight into what consciousness actually is. So who knows? And again, I don't do research on consciousness, nor do I take psychedelics. So I'm one step removed on both of these fronts. So it'd be better for you to ask that question from somebody in the trenches who's actually working on consciousness from a scientific perspective. And there are many researchers who do that. But speaking as someone who knows what it takes to make progress on difficult scientific questions, I will say that we've always found that when you can broaden your perspective on that issue, on that question, see it from a variety of different angles, bring in unexpected links to other qualities of the world, that can sometimes be what it takes to seed a breakthrough. And psychedelic experiences can be one pathway toward that kind of broadening of perspective. It cannot be done in a way that is irresponsible. It cannot be done in a way that isn't carefully thought out and controlled. But if that is the context in which it takes place, then yes, I do think psychedelics potentially have something to offer in our understanding of consciousness. All right, with that, I will wrap it up for today. As I said, I'll try to do your daily equation for Monday, maybe on extra dimensions. We'll certainly meet again next Friday. Next Friday, I think I'm also going to do one of these Reddit public access network things from 2 to 3 o'clock, 1 hour before this. And that may impact how long I go next week on your daily equation. So if you want to start an hour earlier, you can absolutely do that. RPAN, just look it up. And other than that, I will see you metaphorically on Monday, I believe, and in this live session 1 week from today. All right. Thanks for all the questions. Thanks.